So, welcome students. In today's class, we will continue discussion on force directed scheduling. So, in the last class, we have understood what is force and how to calculate the force. So, just to recall, there are two type of force. One is the self force and there is another called this predecessor or successor force, right. So, and then the basic idea is that if we try to schedule a operation Vi in time step L, it will increase the concurrency in the time stamp and it will decrease the concurrency of the other time stamp where it could have been scheduled, right. So, this is I am going to calculate, and also once I am going to schedule this operation in time step L, it might impact the node that is its predecessor and the node that is its successor, right. So, how? Because the time frame of this the successor node might reduce, because this is the last time stamp where this operation can be scheduled. So, that we have understood in detail in the last class. So, the force I am going to calculate for each operation in each time stamp. Okay. So, that something is, so let us say it is already calculated. Okay. So, just to understood now, so this force is something is the concurrency, right, and if the concurrency is high, that means I am going to if I schedule this operation I in time step L, it will increase the concurrency and hence it will increase the resource usage, and if the concurrency is low, that means the number of operation going to be scheduled in a time step will reduce, or the hence it will reduce the concurrency and hence also reduce the number of resource usage in the time step. Okay. So, these analogies let us say we already have. Now, I am going to think about how I can develop this both this list scheduling algorithm MLRC and MRLC, right, minimization of latency under resource constraint and minimization of resource under latency constraint. So, let us now take the recap for the list scheduling algorithm for MLRC. So, here the problem is that you already have given the resource bound for each type of resources, and I have also given the sequence graph, and I am going to schedule the operations. And if you just recap the list scheduling algorithm, what was going to that? I am going to take the timestamp 1, I will identify for each. So, I am going to take timestamp 1, I am going to take the each resource type. So, first say type 1, type 2 and type 3. So, for each type of resource, I will identify what are the operations that is ready to be scheduled in this timestamp. Okay. And also for any other timestamp say L, I am going to identify the operation which is already running, which is scheduled earlier and is still running, right. So, if some operation is already running, I have to allocate resource for that, but and now suppose I have already allocated the resource for the running operations and still I have few resource available in a time step L. Okay. And now what I am going to do, and say there are some few operations are ready to be scheduled in this time step and which is larger than the available resource. So, I have to take a subset of the operations from that available ready operations, okay, and there I have actually used the priority function, right. So, and the for list scheduling algorithm, that priority was from the distance from the sync node. So, and then so I am going to select this and I am going to schedule this operation in the timestamp until my resource bound does not violate it, right. So, if you recall this algorithm, that for each timestamp, basically I am starting from timestamp 1, for each type of resource I will identify the ready operation ready to be scheduled, I will identify the operation that is running in this timestamp L of type k, and then I must schedule this operation TLK, and I am going to select a subset of the ready operation such that my resource bound is not violated, right. So, that is something I am going to do, and that particular this SK is the subset operation that actually start their execution in timestamp L. Okay. And then I will go to the next type of resource. Once all the resource type is already considered for the current timestamp, I will increase the current timestamp to next, and then I will go for the next timestamp. Right. This is how the whole algorithm works, and I am going to complete when my sync node is scheduled. So, if I just think about the force directed scheduling for MLRC, this is the same algorithm. Okay. The only difference is this, the selection. Okay. So, earlier for list scheduling, whatever I have talked about, the priority function was the distance, the distance of the longest path from that node to the sync node, that we have already understood. But in force directed scheduling, this particular selection is based on the force, right, and we have to what is our force. So, I have a force, and force is basically concurrency. So, once I am going to select a subset, I am going to select the operations that will increase the local concurrency that means that has the highest force, right. So, that means I am going to order the nodes in terms of their force, and I am going to select the node that has the high value of force, right. So, what is the analogy here? If I if node with high value, that means it will increase the local concurrency, right, but I have to make sure that I am not violating the latency bound. So, that means if there are some node which become critical to be scheduled in this timestamp that I cannot delay it further, I am going to schedule it even if it has force is less, I am going to schedule it, and then if there are more resources are available, I am going to take the nodes with as highest this force, right. So, this is so basically the just to summarize, the algorithm remain the same, only the selections is changed, it is based on force. Okay. And this is what I have already discussed in the previous class also, that this here this algorithm is very generic and your selection criteria can be different, and based on the different selection criteria you can have different algorithm. And once you actually select this subset of this operations from the ready list based on the force, this become force related scheduling for minimization of latency and the resource constraint. So, I hope this is understood. I am not going to in detail because I mean it is well understood now. Okay. So, now let us move for the other algorithm, the MRLC. So, here the latency bound is given, and our objective was the minimization of the resource, right. So, minimization of resource. And if you recall the algorithm that I have already discussed for the list based scheduling algorithm. So, because I do not know what is the resource bound, what I have assumed that initially I have only one instance for each resources, and whenever I found certain operations become very critical. So, if I do not schedule this operation in this timestamp, then it will increase the it won't support this latency bound, then I may increase the resource and I schedule this operation there, otherwise I do not schedule, right. And if in some timestamp there are some resource available, I am always going to schedule those operations if they are not critical, right. So, if you just remember the operations, again I am starting from the timestamp 1. Now, for each timestamp, for each type of resource, I identify the operations that are ready to be scheduled, and I also identify the operations that are running, and I am going to schedule this running operation must, and then I will identify among this ready list what is the slack value. Slack means what is the till, what is the time frame here still can be scheduled, right, which is basically the current timestamp minus TL, the ALAP time, and if it becomes 0, it is 0 slack, that means it must be scheduled there. So, I have to select the subset of this SLK for where this slack was 0, and if my resource bound is not supporting this, I am going to update, I will increase my resource so that this SK must be scheduled. And if say there is no 0 slack operation and still I have already have some resource, then I am going to select the operations which is has non-zero slack also, but without violating my resource bound. Okay. So, this is how I am going to do it for each type of resource, and then I will increase the time and I will go for the next time and so on until my the sync node is scheduled, right. So, this is the list scheduling algorithm for minimization of resource under latency constraint, right. So, this is basically a very greedy algorithm that I always assume that I have a minimum resource available, and whenever I am forced to increase the resource, I am going to increase the resource, right, and this way I am going to do it. Okay. But this force related scheduling for MRLC is completely different, and it is very interesting. So, here if you remember that you basically I am going to take the timestamp 1, then 2, then 3 and 4. So, in timestamp 1 I identify the operation that can be scheduled in timestamp 1, then I move on to timestamp 2, I will identify the operation that can be scheduled in timestamp 2 and so on, right. But here I am not going to go by the time step wise. What I am going to do? I am going to schedule an operation in every iteration. So, it does not have 2 loops, right. Earlier it was kind of 2 loops. Now, what I am going to do here? I am going to in each timestamp I will identify a operation, I am going to schedule it, and the next iteration I am going to again identify another operation and I am going to schedule it. So, basically this will repeat for order of n, because this loop will execute for order of n, and because every time every iteration I am going to schedule one operation. Okay. And then what I am going to do inside this loop? So, the idea is very interesting. So, what I am going to do, you already remember that for every node there is a range where it can actually can be scheduled, which is by Ts to TL, right, that we already understood. So, this is the time frame. So, for each node I will identify the time frame and then I will identify the operation distribution and type probability, right. So, for each operation I can identify the probability, right, what is the probability of the operation to be scheduled in each time frame, which is basically 1 by mu I plus 1, right, you recall that. So, this so mu I basically nothing but Ts sorry TL minus Ts. Okay. So, so that is already calculated, and then for each time stamp we have already identified the terminological QKL, that each time stamp I will identify the total type distribution of operator type K. So, I am going to calculate all those things, right. So, I will identify the probability, I will identify the probability distribution, and then I will identify the type distributions, and then I am going to calculate the self force and the predecessor and successor force and total forces, right. So, you remember that self force is something I will calculate, because this self force is this operation could have been scheduled anywhere, but if I try to schedule it here, it will impact the concurrency here, 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 here and here, it will impact positively here and negatively here. So, that I will calculate, and then predecessor and successor force is that if I schedule it here, it will impact the overall scheduling of the predecessor nodes and the successor node. I will calculate them, and then this is the total force is nothing but this plus this. Okay. So, the idea is that in each time stamp I am going to calculate the total force for each node. Okay. And basically it is not only that. So, it is basically it is the total force of node I in each time stamp while it is schedulable, right. So, for each node it is not a single value also, for each node also there are many values, because if you will get a value if I schedule it here, I will get a total force if I try to decide to schedule it here, I will get another total value if I try to schedule it here. So, I will have this basically V n into L number of total forces, right. So, this is already I can calculate in this 3 time step. And now, because what is my objective here? My objective here is to reduce the resource, right, my minimization of the resource. So, what I am going to do it now, I am going to select the operation. So, I am going to select the total force which is the minimum. Okay. So, I have n into L number of total forces, and if I say select one such which is the minimum value among all the total forces, and what does it indicate? So, that suppose I have selected TIL, right, that means now operation VI is going to schedule in time step L, right. So, that is what is going to happen here. So, I am going to select an operation with least force among all these total forces, right. So, that is the beauty of this algorithm, that every time stamp I am not going by one time stamp 1, 2, 3 and 4. What I am doing here, I will calculate the total force for all nodes in all possible time stamp. All possible time stamp is basically the time zone or the time frame where it can be scheduled, and then I am going to find out among all these values for all nodes n into L values, what is the minimum value. So, if from the what is the minimum value, say suppose I got this minimum value for TSIL, what does it mean? That now I am going to schedule this operation I in time stamp L. So, basically in every time stamp I decide the schedule of one operations. Okay. And then what is once you fix it, again your time frame of all nodes, successor predecessor node will change, the number of node will also change, because one node is already fixed. So, I have to recalculate the whole thing again for all remaining nodes, right, and again I am going to select the least one, least force, and I am going to schedule that operation in the time stamp. So, this I am going to keep doing it until my all operations are scheduled. Okay. So, you already understood that in the previous class that this is order of n square, because of this predecessor calculation, this predecessor force and successor force calculation was complex. So, it is n square. So, the overall complexity of this algorithm is order of n cube. Okay. But this algorithm is completely different from the MRLC algorithm, which is based on the list scheduling, because here I am not going by time step wise, I am going operation wise. And how does this guarantee that it can meet by latency bound? Because all this value is calculated, the time frame, everything based on this lambda, right, because this is, I mean, if a lambda must be greater than of its ALAP, if it is greater than of its ALAP, or if it's the schedule is does not possible by lambda, it will say it is not feasible, right, by your ALAP start way. So, since all this value is getting calculated considering this lambda is for this lambda it is feasible, and I am not scheduling any operation beyond his time frame, right. So, whatever the time frame is given by ASAP and ALAP, I am going to schedule this operation one of the time stamp. So, it ensures that the way I am scheduling it never violated by lambda, because this lambda is already validated by TLAP and TSAP, and then whatever the time frame I am considering for the operations, all are actually supporting this lambda, and hence what the schedule that is going to happen, it always may satisfy the time bound, okay, or the latency bound. So, what I have understood that this does not take the operation one iteration at a time, rather it take one operation at a time, right. The operation with the least force is scheduled in that corresponding time stamp. And what is the idea here, why I am taking the least one? Because I want to reduce the minimization of resource, right. So, the minimization of the local concurrency, if I take the least force, that means it will it has the minimum impact on the concurrency, and since my objective is to reduce, because the concurrency is basically the number of resource, right. If there are 3 operations is running in a time stamp, that means I need 3 resources. So, but if the concurrency is less, say 1, that means I need 1 resource. So, if I reduce the concurrency, right, so then my resource requirement will be less, and so that is why I am going to select the operation with the least force, right. So, that means it is actually giving me the minimize the local concurrency, and which is nothing but the minimization of resource, right. So, minimization of local concurrency is nothing but the minimization of resource. So, selecting the operations by the least force ensure that it will actually minimization of the resource, okay. So, that is the overall idea. So, in summary, so we have understood 2 algorithms in today's class. One is the least force directed scheduling for MLRC, minimization of latency under resource constraint, and we have understood that that is the same algorithm which I have talked about for least scheduling, and only thing is that my selection criteria here based on the force, and I am going to select the node which has the highest force, because my objective is to reduce the latency and hence increase the concurrency, right. If you run many nodes in parallel, my latency will automatically decreases, right. So, that is the analogy there. But for this MRLC, whenever the latency bound is given, you want to reduce the minimize the resource. The idea here is that you take you schedule one operation at a time which has the least force. So, that means I am going to every iteration I am making sure that I am increasing this concurrency by minimum way. So, and hence my algorithm will give me the minimization of resource, okay. So, and we have seen that complexity is order of n cube. So, whatever is found that this results given by this force scheduling is much better than the least scheduling, but only thing is that the complexity is quite high, because in least scheduling it was order of n and here it is order of n cube. So, for this MRLC, so for large graph it will take more time compared to this, right. So, although it gives very good results, better results than scheduling, but sometime this because of the complexity it may not be applicable to for very large design, but for smaller design it always give me better result than least scheduling, okay. So, with this I conclude today's class. Thank you.